All right, we're going to start chapter 6 with a discussion of angles, and then in the next section we'll get into more transcendental functions, which we call the trig functions. But many of the trig functions use angles as their argument, so we're going to describe angles and how to measure them. The first angle that I've got up here we call angle alpha, Greek letter alpha, and notice that the vertex is at the pointy end, and then we have two rays. I have an arrow that goes from what we call the initial side up to the terminal side. And because that arrow is going in a counterclockwise direction, we say that our angle alpha is positive because it's counterclockwise. We can also draw negative angles. So here is a negative angle, which we can call beta. And this time the arrow is going to go from the initial side to the terminal side. And it's going in a clockwise direction. So we'll call this angle beta, and notice that angle beta is a negative angle because it is clockwise. Let's put these angles in standard position using our axes. So here's the x-axis and the y-axis on our graph, and it appears that alpha is an acute angle. So in standard position, the terminal side would be in quadrant 1. So alpha is in standard position. And that means that the initial side is on the positive x-axis. The vertex is now at the origin. And so we say that alpha is in standard position. We can also draw our angle beta, or negative angle beta, in standard position. The initial side would be the positive x-axis. It appears that the terminal side would be in quadrant 3. So we'll come around this way. And there is our angle beta, also in standard position, with the little arrow going in the negative direction or clockwise. We also have a definition of what we call quadrantal angles. So if we have a quadrantal angle in standard position, the terminal side will always be on the x-axis or the y-axis. So in standard position, with terminal side on the x or the y-axis. So a picture of, say, a quadrantal angle may look like this. Okay, there you have the initial side on the positive x-axis and the terminal side on the y-axis. Or we could go in the negative direction and maybe go around again to the y-axis. those would be examples of quadrantal angles. So anytime the terminal side is on one of the axes, it would be what we call a quadrantal angle. Now, measuring angles, either degrees or radians. So angle measure in degrees. We say that there are 360 degrees and one counterclockwise revolution. We say that 180 degrees then would be half of a revolution, called a straight angle. Uh, 90 degrees we call a right angle. And we can break degrees down into smaller units called minutes. So 1/60th of 1 degree is equal to 1 minute. And we use a little hash mark there for 1 minute. And 1/60th of 1 minute we define as 1 second. So we have two little hash marks there. That's 1 second. Well, using these measurements, let's see how we can change decimal degrees into minutes and seconds and vice versa. So first example, suppose we have 121 degrees and 13 minutes and 54 seconds. And I would like to have that in decimal. Well, I'm going to start working from the outside with the 54 minutes. And it turns out that I can divide by 60. And I'll come out with the equivalent in minutes. Turns out to be 0.9 minutes. Okay. So our intermediate results then are 121 degrees, 13.9 minutes. And I just do this again to change the minutes to decimal degrees. So 13.9 times 1/60 is 0.2317 in degrees. And so my final results then is 121.2317 degrees. So there you have the minutes and the seconds up here changed to decimal degrees. We can go in the opposite direction. Suppose I'm starting off with decimals and I want to change it to minutes and seconds. Suppose I start off with 48.1234, all in degrees. And I want to change this to minutes and seconds. Instead of dividing by 60, you're going to be multiplying by 60. So we start off 0.1234 times 60. And that will give us 7.404. And that's going to be the minute units on the degrees. And then we want to change the 404, 0.404, again, multiplying by 60 gives us 24 seconds. So our final result is 48 degrees, 7 minutes, and 24 seconds. So those of you have examples of changing from decimal degrees to minutes and seconds. You can do this very quickly on your calculator. Now the other kind of angle measure that we'll use probably most of the time is called radians. And you'll find that on your calculator you have a radian mode and a degree mode. But a radian is much larger than 1 degree. So let's see how it looks on a circle so we can kind of compare the size of a radian to the size of a degree. So here's a circle. And I'm going to draw, say we have radius r. And I'll put an angle in here so that the arc along the circumference is equal to the radius. And then the angle that subtends that arc is equal to 1 radian. So we have the central angle. The lights just went out, Richard. Theta. And theta subtends an arc of length r, where r is the radius of the circle. So you can see that this angle is much larger than, say, 1/360th of a rotation. In fact, it looks like it might be close to 60 degrees. We can say that 2 pi radians is equal to 1 rotation. In other words, 2 pi is equivalent to 360 degrees. And pi then is going to be equivalent to 180 degrees. Now 2 pi radians is going to be 1 rotation because if I go all the way around the circle, I will have 2 pi radians in the central angle. We can convert degrees to radians using this is our conversion factor. So if I have 18 degrees, I can multiply that by pi over 180, and I'll get pi over 10 radians. In the other direction, I can take radian measure, say 2.5, and multiply it by 180 over pi, and the decimal equivalent is approximately 1.43 radians. Excuse me, 143. Sorry, 143 degrees. Okay. So 2.5 is going to take you over into the second quadrant, which would be about 143 degrees, and this is all rounded quite a bit. Just to get a feel for what radians sizes are. Let me just do one more picture over here. If we start here at 0 radians, this would be pi radians, or equivalent to 180, and then back here would be 2 pi. That would be a complete rotation. This would be pi over 2, or approximately 90 degrees. Here we would have 3 pi over 2, which is 270 degrees. Now if I just change these pi's to a decimal number, pi of course is approximately 3.14. 2 pi is approximately 6.28. Pi over 2 is approximately 1.57. And 3 pi over 2 is approximately 4.7. So if you're talking about radians, 3 radians in standard position would have a terminal side in quadrant 2, whereas 4 radians would be have a terminal side in quadrant 3. One of the shortcuts we take when we're describing angles is just to say where the terminal side is. We might say that if we have an angle of 120 degrees, it's in quadrant 2, which means that the terminal side is in quadrant 2. Whereas if we have an angle of minus 120 degrees, we would be coming in a counterclockwise direction, and that would put us again in quadrant 3. So minus 120 degrees would be around in quadrant 3. Or if we're talking in radians, we could say 1 radian is in quadrant 1, which means the terminal side is in quadrant 1. Negative 1 radian would be in quadrant 4, which means that the terminal side would be in quadrant 4. Okay, so now let's do some problems using some of these angles. Here's a picture of a circle once again. And we're going to have, well, I don't want that circle like that. We'll just make it a circle and draw a central angle of size theta. And we're going to say the radius of the circle is r, and the arc length subtended by that angle we'll call s. Radius r, s is arc length, and theta is our central angle. We can set up a proportion that says the circumference of the circle, 2 pi r, divided by the central angle, 2 pi, is proportional to, in this picture, the arc length s divided by the central angle theta. And with a little algebra here, we come out with a formula for the arc length s equal to r theta. But theta has to be in radians. So in order to calculate arc length, we have to have the central angle in radians and the radius. So an example might be, suppose we're given an arc length this time of 6 centimeters, okay, and a central angle given in degrees of 120 degrees, and we're asked to find the radius of the circle. Well, the first thing I'm going to do is change that 120 degrees to radians. Okay, so 120 degrees times pi over 180, and that gives me 2 pi over 3, and this then is the radian measure. And now we can put it in the formula, S equals R theta, S equal R theta. We have 6 centimeters equal to R, and then our theta, 2 pi over 3. And we just multiply by the reciprocal of our angle here, and we come out with R equal to 9 over pi. And this is going to be in centimeters. And that's the exact answer. If we want the equivalent decimal approximation, we can put that in our calculator, and we come out with 2.9 centimeters approximately, rounded to 1 decimal place. So that's an example of using our arc length formula. Another formula that is derived from that is called the linear velocity. And we're talking about the linear velocity of an object that is going around in a circle. So this would be about v. We'll use the letter v for that. For an object traveling in a circle. At a constant rate of speed. Now remember that we have learned in the past that distance is equal to rate times time. Okay, and so we're talking about a rate, and so we can say that our velocity v is going to be the distance traveled on the circle divided by the time that it takes to cover that distance. So the units are going to be things like miles per hour or feet per second or maybe meters per second and so on. Now angular velocity is something we haven't discussed before, and that is the speed that the angle, the central angle, is changing in the middle of the circle. So angular speed, which we call omega, is equal to the change in the angle divided by the time that it takes for that angle to change. And we also have another formula that we've talked about, v equal to d over t. So this is angular speed, and this would be the linear velocity of the object on the circumference of the circle. Now we can substitute in here S equal to R theta, the arc length formula that we learned earlier, or we can say the distance along the outer part of the circle is equal to the radius times that central angle, and substitute it into our formula over here. So then we have v equal to R theta over t. The R theta has been substituted for the distance along the circumference of the circle. But we know that the angular speed that the angle is changing in the center of the circle, is theta over t. So that gives us the formula then, v equal to R times omega. I'll put that in a box. This is linear velocity of the object on the circumference of the circle equals the radius of the circle times the rate that the central angle is changing, which we call the angular velocity. Now this angular velocity has to be in radians. Per some time unit. Okay, so let's do an example where we're going to use the formula for linear velocity. And I have an example here. say we have a wheel that's rotating at 10 RPM. Now, RPM is not radians, it is revolutions per minute. So don't mistake that R for radians. That is revolutions per minute. And we have a radius of this circle, this wheel has 4 feet. And we want to find the speed of the current in the stream that is pushing this wheel around. So actually it's the same as finding the velocity of a point on the circumference of that wheel. So to find the speed of the current, we're simply going to use our formula down here, V equal R omega. And we have the 4 feet that we can put in for R. And omega needs to be in radians. So let's think about that. We have 10 revolutions per minute. But how many radians are in 1 revolution? 2 pi. I'm off the screen. Okay. So, well, let's stick it here then, and then we'll move back. So there are 2 pi radians in 1 revolution. Is that on there? No. Okay. So let's put it down below then. Okay. So V is equal to 4 feet. We have 10 revolutions per minute. And we're going to multiply that by 2 pi radians per 1 revolution. So we're changing the revolutions into radians right here in the formula. And I just plugged that into my calculator. I came out with 251. This is approximately. And we're working with feet. The revolutions are gone, and so we end up with feet per minute. So that is the velocity of this stream that's pushing the wheel around, 251 feet per minute. Now, if we're asked to change this to miles per hour, it's simply a unit change, and I'll just set it up for you. We're going to have to change the units in the feet to miles and the minutes to hours. So to change to miles per hour, I start off with 251 feet per minute. And I know that there are 5,280 feet per mile. So that takes care of the feet, but then we want minutes to be in hours. So there's 60 minutes for 1 hour. And again, plugging those numbers into my calculator, I come out with 2.86 miles per hour. But that's simply a unit change from feet per minute to miles per hour. So our second answer, 2.86 miles per hour. The last problem that we want to do is an area problem for the segment of a circle. And we have two options for solving this sort of problem. One is to use a new formula, the area of a sector equals 1/2 r squared times theta, where again theta is in radians. So my situation is I'm given a central angle of 50 degrees and a radius of 2 feet. And we want to know how big a sector is subtended by this arc. So the picture looks like here's a 2-foot radius and about 50 degrees in here. And we want to know what the area of that sector is. So we can plug in what we have in our formula that's given here, 1/2 r squared. And then again, 50 degrees has to be changed to radians. And plugging that in my calculator, I come out with approximately 1.745. And we're talking about feet, so this would be in square feet. The other way to solve this problem is to just go straight to a proportion that works in the circle. We have the area of a sector over the central angle that is subtending it is going to be proportional to the area of the circle and of course that's subtended by 360 degrees. So if we put in what we know, the area of a sector is what we're trying to find, is equal to the area of a circle, which is pi r squared, divided by 360, and multiply both sides by 360, by 50, beg your pardon, and you'll get the same result, 1.745, and this is in square feet, once again. So two options for solving this problem: use the new formula, or just set up a proportion of the area of the sector over its central angle equal to the area of the circle divided by the 360, which is a total revolution. That's it.